Hello everyone. Today we shall discuss about hello everyone. Today we shall going to discuss about kinetic theory of gases and see how we are going to see this kinetic theory of gases. You can see here that in kinetic theory of gases we will all deal with such things. The first one is the unseen engine. How the random dance of atoms creates the world we see. It all starts with a simple question: what is pressure? We experience it every day. It keeps a tire inflated and a balloon from collapsing. We can measure it, predict it, and use it. But what is it fundamentally? For centuries, we knew the rules of the game. Boyle's law, Charles' law. Boyle's law, that is constant temperature, pressure varies inversely with volume. Or you can say PV equal to constant. You see, this is the pressure, this is the volume, and this is the graph we get from Boyle's law. You see here, this one. This is Charles' law. At constant pressure, volume is proportional to absolute temperature. You see, this is the volume, this is temperature, and V varies as temperature. Therefore, this is straight line starting from the origin. That is Charles' law. Now we learn these things to understand why we must look deeper. All things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are little distance apart, but repelling upon being squeezed into one another. This is given by Richard Feynman. So we can say a radical idea, the kinetic theory of gases. First, numbers, constant motion. A gas consists of a very large number of molecules in incessant random motion. Negligible size. The molecules are point masses. Their size is negligible compared to the average distance between them. Perfect elastic collisions. Molecules collide with each other and with the container walls without any loss of kinetic energy. Pressure is the relentless force of a billion tiny collisions. A molecule hits the container wall and rebounds. You see, in this way, its velocity component is reversed, which is mvx, this will be minus mvx. This change in velocity is a change in momentum. Pressure is the total momentum imparted to a unit area of the wall per unit time. Then we can say the momentum transferred to the wall is del P, change in momentum equal to 2 mvx. From individual impacts to a collective force. See here the macroscopic pressure we measure is capital P. Number of molecules per unit volume is small n. Mass of a single molecule is small m. And V square, the mean of the squared the speed of the molecules. Therefore, P can be written as 1 by 3 Nm V square. The steady pressure of a gas is the average result of the chaotic motion of its molecules. Temperature is the motion of atoms. From kinetic theory, we get P equal to 2 by 3 capital N, 1 by 2 mv square. And from observation, that is from ideal gas law, P equal to N kBT. Equating the two reveals stunning connections. Average kinetic energy half mv square is equal to 3 by 2 kb to T. This one we are getting that half mv square equal to 3 by 2 kb into T. Temperature is a direct measure of the average translational kinetic energy of the molecules. The insight changes everything. The internal energy of an ideal gas depends only on its temperature. At the same temperature, molecules of different gases have the same average kinetic energy. Practical implication 1 by 2 m light v square equal to 1 by 2 m heavy into heavy whole square. Practical implication. This means latter molecules must have a greater root mean square speed. For argon 39.9 U and chlorine 70.9 U. At the same temperature, the ratio of root mean square speed is V of argon and V of chlorine is 1.33. The principle of equal shares, the law of equipartition of energy. In thermal equilibrium, the total energy of a system is shared equally among all its available energy modes, degrees of freedom. Each degree of freedom gets an average energy of half kb into T. If you see that monoatomic, there are 3 translational motion. In case of diatomic, 3 translational motion and 2 rotational motion. And the vibrational modes gets kbt. This is in the vibrational modes. So each degree of freedom gets an average kinetic energy of 1 by 2 kb into T. From a simple rule, powerful predictions, logic, total energy is equal to mole into degrees of freedom into half RT. This is the logic. Molar specific heat at constant volume is a change in energy with temperature. We know that's equal to d by dt. From predictions we get here, the gas type, derivations and predicted Cv. Monoatomic U equal to 3 by 2 RT. Cv, we know that d by dt, the way getting 3 by 2 R. Predicted Cv is 12.5 joule per mole per Kelvin. For diatomic, phi U equal to 5 by 2 RT, therefore Cv equal to du dt 5 by 2 R. That's what we're going to get 20.8 joule per mole per Kelvin. In this way, you can find the logic and the predictions from simple rule to powerful predictions. The ultimate test, theory meets reality. Gas, this is gas, various type, predicted Cv, measured Cv. For helium, it is monoatomic. Predicted Cv is 12.5 joule per mole per Kelvin. Measured Cv is 12.5. Neon, monoatomic. Predicted Cv is 12.5. Measured Cv is 12.7. Hydrogen, diatomic. Predicted Cv is 20.8. Measured Cv is 20.4 joule per mole per Kelvin. For nitrogen, it is diatomic. Predicted Cv is 20.8. Measured Cv is 20.8. Oxygen, diatomic. Predicted Cv is 20.8. Measured Cv is 21.0. The agreement is remarkable. The unseen engine behaves exactly as predicted. A final puzzle. The root mean square speed of a nitrogen molecule is faster than sound. The root mean square speed of a nitrogen molecule is faster than sound. So why does it take several minutes to smell a perfume from across a room? This is the final puzzle. The RMS speed of a nitrogen molecule is faster than sound. So why does it take several minutes to smell a perfume from across a room? The journey is not a straight line. The concept. Molecules have a finite size and constantly collide, deflecting each other's paths. Definition. The mean free path is the average distance the molecule travels between collisions. And the formula is L equal to 1 by root 2 n pi d square. For air at STP, mean free path L equal to 2.9 10 to minus 7 meter, a molecule collides billions of times per second. So you can say that a molecule collides billions of times per second. The unseen engine is all around us. The stable, predictable world we experience is the direct result of chaotic, random dance of countries, countless atoms. The kinetic theory gives us the language to understand this hidden engine, revealing the beautiful simplicity that underlies our complex world. So, this is the kinetic theory of gases. Again, the conclusion is the unseen engine is all around us. A stable, predictable world we experience is the direct result of the chaotic, random dance of countless atoms. The kinetic theory gives us the language to understand this hidden engine, revealing the beautiful simplicity that underlies our complex world. Dear friends, if you like this video, please subscribe, like and share. Thank you everybody for watching this video.